Okay, everything's recording that should be recording. I think we're good. Can everyone still see my screen? Kind of lost on GDB 8. All right, so let's jump into it. So first question is kind of lost on GDB level 8. Been trying to do stuff with handling. So let's take a look at that. So debugging refresher, GDB level 8. Let me know if it stopped showing my screen for some reason. I was having that problem last week. So if that happens, just yell at me. All right, so we're taking a look at Embryo Gdb Level 8 to go ahead and get started here. Just as a quick, I guess, like intro on the Embryo Gdb challenges, if you haven't seen them, if we go Rev 18, I'm not going to solve Rev 18, but I can certainly talk about it. Okay, so basically we can run this challenge, and it's going to go ahead and launch up GDB for us. Now, I have Gef installed. If you don't have Gef installed, I would highly recommend looking into using it. It's great. It's a little bit overwhelming, I guess, initially, but once you sort of get used to using Gef, it becomes really, really useful because it just kind of shows you everything. You don't have to dig through all of the arbitrary commands, and instead everything just kind of works. So, this in mind, if we run our challenge, I guess that's right. Also, if you use Gef in these challenges, you can run into issues where you sometimes lose the printouts. So let me really quick get rid of that. I think that works, right? Yeah, there we go. All right. So yeah, if you have that problem, just make sure you comment out the line in Gef with your GDB init. So if you have Gef installed, don't use it for this. Forgot about that. So let's quickly review this level. So as we've already demonstrated in the previous levels, GDB has basically full control over the target process. And essentially, what we're going to try and do is you can see what happens when you run the command like call void win. And so if we go ahead and look at this, just call void win, and we do this, then GDB, let's see, so this program being debugged, signaled, using the frame when the signal is received to change the behavior, set on when signal on. Evaluation of this expression will be abandoned when the will silently stop. All right, well, let's see what happens when we listen to GDB. So as you can see, we've called win, and we are getting this segmentation fault. And so the question becomes, why are we getting this segmentation fault, and what can we do about it? So now that I've already got the printouts for the challenge that I wanted, I'm just going to go ahead and put them in like a file. So new text file, and I'm just going to dump them here and leave them there. So if we need to refer back to kind of our write-up, we can do that. And for me, I'm just going to jump straight back to Gef at this point, now that I know what the challenge is doing. And it's just because I'm used to debugging with Gef. It's the workflow that I'm used to. If you're not used to debugging with Gef, all you have to do is just like basically print out all of the extra data that Gef gives you, which is just examining your registers, looking at the instructions that you're about to execute, and also looking at like your stack memory and stuff like that. And so we saw that the program basically wanted us to run it and then attempt to call win. And if we do this, Gef is going to give us a nicer printout where we see that we have crashed with the reason of sigsegv, so that's going to be our seg fault. And it's also going to tell us that we've seg faulted right here on this instruction, which is move EAX, and then it's dereferencing RAX. And if we take a quick look at this, we can see that at the time of the crash, if we come look at our registers, RAX was 0. And so if you weren't using Gef and you wanted to figure out this information, what you would do is you would come in here and say, okay, well, my process has stopped at this address for the reason of sigsegv. Vanilla GDB will give you this information, as we saw. And if you look at the instruction that you're currently executing with x/i RIP, we can see that this is the instruction where our program has stopped. And so we have this move EAX, dword pointer RAX. And so the next question to me is, whenever my program segfaults and I know the instruction where it segfaults, the question to me is going to become, well, why did it segfault? And so this is not like there's not like a one way to do this. It depends on the instructions that you're running into. But in this case, knowing the knowledge that we have about assembly, we have move EAX. Okay, that's pretty standard. And then we have this dword pointer RIX. And so what this instruction is doing is trying to load an integer from this pointer at RIX into EAX. And if we go and look at what the value of RIX actually is, if you're in vanilla GDB, you could do info registers, and we can see that RIX is clearly 0 at the time of the crash. And so this means that we are basically dereferencing a null pointer. And so the question becomes, well, why are we dereferencing a null pointer? And can we do anything to stop this from happening? And so let's not do that. So now let's go ahead and take a look. So if I'm going to type disas to disassemble, and we're going to disassemble win and take a look at what's going on. And so right away, here's the top of our function, and then we can read out exactly what happens every single place. And as you can see, that it looks like there's actually quite a lot going on. But we can see that there's a puts, there's an open, it looks like we're jumping around the win a little bit. And if we're kind of curious of what this function's doing, I know that there's basically two kind of directions you can go here, depending on I guess what kind of reverser you are. You can either say, I only care about this immediate crash here, or you could try and understand the function a little bit more. I'm personally someone who will prod around a little bit more to see if there's extra information that I can pull out. For example, we can see that we have LEAs followed by puts, and then gef is nicely printing out the exact address that it's rip relative addressing. So we can always XS the strings that are being puts to us. So you can see that very clearly we are going to go ahead and just be winning at this point. And so you can win. Here's the flag, assuming that he's going to try and open /flag and do that. And so now that we kind of know that it's probably doing what we expect it to do, the question is well, why is RIX 0? And what is EAX going to be used for in the future? And if we actually look at this function and kind of look at where EAX is used, we can see that it looks like we're pulling this stack value off. So we're literally moving 0 to this location on the stack. So RBP minus OX8. And then we're loading it from the stack at RBP OX08 or OX8 into RAX. So these two lines right here are essentially storing a 0 on the stack and then putting it in RAX. And then right after that, we're dereferencing it. So instantly that tells me that something probably needs to change in this region, because we've got the 0 that's getting stored on the stack and then loaded into RAX and then instantly dereferenced. And so we need to find some way to dodge this. Now, based on the fact that you're in the last level of Embryo GDB, you probably know a couple ways to actually solve this problem already. For example, we could we could knock out this instruction to maybe avoid this dereference of RAX, or maybe we could alter the value that's being loaded so that maybe it's valid, etc. And so let's try and figure out explicitly what's happening here. So it looks like we're dereferencing RAX to load into EAX, and then instantly dereferencing that +1 to get EDX. And then it looks like we're storing things back on the stack. So it looks like this RBP minus OX8 value is clearly relevant. So as we can see, we store the 0 there. We move it once out. We move it twice out. Seeing if we see it anywhere else. We don't. All right. So we're going to load that in. We're going to store EDX here. So this to me is kind of looking like our interesting chunk of code. So we've got these kind of 6 lines to deal with. And personally, when I need to focus on something like this, I'll just pull it into a notepad document and start playing around with it. So at this point, really what you need to figure out is what specifically these 6 lines are doing, and can you avoid this somehow or skip over it? We can also see that once we get past that, we probably should be fine. And we could try to confirm this theory. We could, instead of calling win directly, maybe we could try and call deeper into win to try and bypass this. So maybe our suspicion is that if we get to this specific LEA, then we should be fine. So we could take this address that LEA is at, run our program, and instead of calling void win, we could instead try and call, what is the way that you call a static offset in GDB? Or do you have to call a symbol? You actually might have to call a symbol. But what we also, so I guess the way that I would probably confirm that these 6 lines is maybe overriding the first one with a jump over them. Yeah, I can jump to a rip relative. So let's just try that. Set RIP equal to that, and then SI. All right, yeah. It's probably not going to like it if we just casually jump into the middle of the function, generally. So in that case, let's go ahead and do this the fun way. So let's break it win. Let's run. Let's call win. And so now we are broken in win after setting up the function. And so let's see, have we subtracted 10 from RSP yet to make room on our stack? Nope. All right. And so here's our problematic 6 kind of lines that we're going for. And so now let's see if we try and jump over them. So set RIP to this value, and then let's SI. All right, we're still seg faulting. But basically, those 6 lines are where your problem lives. If you're looking specifically for what you need to do, I would recommend experimenting with some of the values in here and seeing if you can get around that. And if, I guess, do you need more specific help than that, or is that enough for you? I can go from there. All right, gotcha. But yeah, the main thing is just like when you run into situations like that, your first instinct should not be to try and handle the seg fault and just ignore it and keep going. Instead, you should be examining why the seg fault happens and seeing if you can avoid it. Note that dynamically changing your program like this isn't something that you will often do in GDB, but instead, like the main thing here is that you're doing root cause analysis. You're trying to figure out why you're crashing and what the solution is. And then you can test it live in GDB by byte editing your code. All right, so the next question was about Rev 18.0. And Rev 18.0 is one of the last levels in reverse engineering. And so let's go ahead and take a look at that one really quick. Load everything up. Don't need this anymore. All right, so /challenge, baby rev level 18. So in baby rev level 18, you are continuing down the rabbit hole that is Yan 85. And in Yan 85, you are basically given a custom architecture and VM that you have to reverse engineer and figure out how it works. Now, if you're at level 18, you presumably already have a decent understanding of how Yan 85 works. And all this is asking you to do is input your Yan code and get the flag. And so I guess what specifically are the pain points that you're running into with 18? Because this is a fairly straightforward challenge. It's just kind of a challenge to actually get from point A to point B here, but the path is pretty obvious. Push the flag into the code. All right, so my advice would actually be to do something a little bit different on that, because one thing that you've probably noticed is that in some of these earlier Yan 85 levels, we're executing Yan 85 code. And so let's go take a look at which one would have something like this. Maybe 17? what I would recommend doing is looking at some of the earlier challenges and seeing how they are manipulating strings around in their yarn code to get some inspiration on how to do it. Because uh, in this one, we're giving you yarn code. And so let's see. I really want to open this in Ghidra, so let's spin up the Ghidras. But before I do that, let's quickly demonstrate. So if we actually take a look at all of this massive amounts of code, and whenever you're dealing with something like this, I'm going to dump it into a text editor so that I can like search through it easier. But as we can see, we inputted some arbitrary random value into 17, and as an output, we got this incorrect string. And the question you could ask yourself is, where does this incorrect string come from? Because it turns out that we actually assemble it in the yarn code. And so you can actually look at how that's happening if you look at this write. So we have, I guess it's specific to how this specific instance of the challenge is, but we have a write syscall that is writing from a buffer that's in the yarn code. And in that yarn code, we have assembled this incorrect string. In fact, if we look at the hex values for this string, so let's see if I can do this in one try. For C in this, put a byte here, print a word of the character. No. That. There we go. And then I want those in hex. So if we can take a look at the ASCII values that we're getting, we can see here's the stuff that we're running into. And if we look for this hex 21 value, oh, it doesn't show up. Are we mangling the string? All right, maybe we're mangling it. But yeah, it's mangled and shuffled. All right. But the point is that you can with this operation that they're doing, you can very quickly notice that they load things into memory repeatedly just by basically doing you load an immediate, you set the memory, and then you increment the pointer. And so you can run into you can basically get into this loop where you load some immediate. So maybe immediate A equals OX49, because we want to put an I in there for some reason. And then you would want to store that in your memory somewhere. Because remember, like fundamentally in all the programming languages that you're interacting with right now, at least in this class, your string is just a null terminated series of bytes. And so if we have that 49 and then we store it in our memory, and then following that is a null byte, if you did a syswrite and then gave it the address of where you stored this, you would get that I coming out, and it would be a valid string. Similarly, if you tried to open this, then it would probably try and open I. And so all you have to do is just use those the STM, the LDM, basically use your Yon85 memory to do this. There's some other insane solutions. You can use, I've seen people use like string addresses that are already existing in the binary, stuff like that. But specifically, I would just look into using the Yon85 memory. It's pretty much the simplest way to do it. Does that help or give you any intuition? Awesome. But yeah, you can use the previous ones. I think even like level 14 probably has like a really simple example of this. Maybe we can get lucky. Ah, yeah, here you go. So in this one, you can see that we're printing out like the I, and then the N, and then the C, and then the O, etc. And here we're basically literally just doing an immediate, then you set the memory to this, and then you call your syscall, and then write that buffer out. And so basically here we're just setting one character over and over again, but if you instead set up like a string of characters in a similar fashion, it would work. All right. Next questions. Anyone got other things they're working on? How's Baby Rev going? Would highly recommend starting on Baby Rev as early as physically possible. It's a doozy. Stuck on trying to get the offsets for Rev 9. All right, let's take a look. I guess we should do these in practice mode most likely. And then feel free to like queue up your questions and then I can answer them in succession too. All right, so let's wait for this to reload. All right, so if we take a look at Baby Rev level 9, this one is quite an interesting challenge. And basically what this challenge lets you do is, rather than attempting to actually break the license key, it instead lets you patch bytes in the program. And so you give it an offset hex to change, and then we change those bytes. So for example, if you give an offset of 0 and then a new value of 10, then it tells us that that byte has been changed. Now, specifically to drive home a point about what's happening here, I'm going to open this up in GDB. So I do want to see the output though, so I'm going to disable Jeff for a second. So if we run this challenge and just put in offset 0 and then a new value, just 1 maybe, we can see that we're given an address and it says the new byte has been changed and here's our address. And if we look at the mappings for the program, oh, I can't, info map. Robert, what's the command help to display memory mappings in vanilla GDB? Info proc mappings, that's what it is. No, info procs mappings. Yeah, that's what it is. All right, and so if we look at, thank you for that. I'm so used to using gef at this point. If we look at the mappings of our process, we can see that our challenge has been loaded in at this specific address that it's giving us. So here's our start address. And then if we go look at what the program gave us, where is it? Right here. And so we can see that this start address of the first basically place the binary is loaded in is the same as what it's giving us. And this can also be extended by the fact that if you actually open up this binary in a reverse engineering tool, you can see those exact offsets. And so we change the very first byte to a 1. And so if we take a look at this, I guess xgx this, we can see that that least significant byte has been changed to a 1. And so the question becomes, well, how do you find your offsets? And the nice thing is because our code is basically living in this binary, it's not going to be moving around relative to itself. Instead, the challenge might be loaded in at a different base address, but we know that all of the offsets are always going to remain the same, since after all, it's not like we're changing our file every single run. Instead, it just loads this binary into memory and then does all of its stuff. And so, let's quit. Do I want to quit out of this? Yeah, let's quit out of this. And so if we can take a quick look at this. Now, you could do this in a reverse engineering toolkit. Let's make this very obvious. Let me, I guess, show that really quick. Because I'll show two ways of finding these offsets because I think it's kind of interesting. How long will this take? All right, too long. Let's do it like this. Let's download this. Mainly done it in the GDB. Location I want to change minus the base address. But I didn't know about that mapping. Okay. Yeah, so that mapping is something that you can access in GDB, but if you're outside GDB, you don't have access to that, unless you obviously like put in a 0 for your offset and then just steal it from the first one and then accept that you can only change 4 bytes, but maybe not the best solution. Let me quickly pull up my Ghidra on my local system and I will show this off. All right. So I loaded up this binary and then we are going to change it to this. And then let's change it on Discord. So we use an insane setup now. And I want to stream this window. All right. Hopefully everyone can see that. Okay, so looks like everything is good to go. So if we take a look at this, and if you look at this very first set of bytes that we're getting at the very top, so in your listing view on the left here in Ghidra, this is basically displaying to you the bytes of your binary. And essentially it's going to try and disassemble and interpret all of them. And if we look, we can see that Ghidra's base address for this binary is this 0010000. So essentially hex 100,000. And this is the base address that Ghidra has gone ahead and assigned our binary. And so we need to keep in mind that everything is going to be relative to this base address. And so whenever we see the offset of 100,036, instead it's just 36. And so now we can begin looking at maybe the things that we want to change. So for example, in main, let's say that rather than me wanting to solve the challenge, let's just say that I want to do something insane and let's crash the program. So let's see. So here's our loop of offsetting of the things that we can change. So the first thing that I guess might not be immediately obvious is you can only really change stuff that happens after you actually do the changing. Like if I edit the bytes for this put statement up here, I'm never actually going to reach it because I'm changing it here after I've executed this statement. And so we would be looking for things that are in here. And so, for example, one thing that we could try maybe is we can see that here we move this hex 1D value into this move. What happens if we change this to maybe a really large value and then try and crash the program by reading into it? So let's experiment with that for fun as just a little example. So here we can see that our instruction has this specific offset, which is 101FC7. And Ghidra has this nice feature where if you like mouse over it, I don't think my pop-ups are showing up anywhere on the recording, but if you mouse over it and just leave your mouse there, it will show you a couple different things about this. So it'll give you the base offset and it will also give you the function offset, which can be really nice and handy. So when I mouse over this, I'm literally getting a pop-up that says the image base offset is plus 1FC7, which is exactly what I want. And so that 1FC7 value is that value that I'm looking for. Now, the other things that you might want to confirm about this is you might want to make sure that this is reading an integer instead of a byte, etc. Make sure your kind of data types are all lining up. But let's try and change this 1D value that is living in this instruction. Now, to be specific, we need to figure out which what the specific bytes for this actual instruction are. And this is much easier to do in IDA, but where is it? So we got to open up. No, that's not it. How do I get the actual raw bytes in here in Ghidra? Come on, there's got to be a way. Aha, bytes. There we go. So if you come up here to window and then bytes, we can go ahead and come in here and look at this. And if we take a look at this instruction, Ghidra's going to put a little black thing right here, right where this instruction starts. And if we counted this out, we can see that we're at 101FC0 over here. It probably is really hard to see on the stream, but just because the font size is really small, I don't think I can change that. But essentially we can see that our instruction is starting with BA, and then we see 1D. And if we go to our next instruction, it starts at that 48 over here. So it's looking like that we have this BA, which is that move EDX. We could assemble this and look at this if we really wanted to confirm that, but then we have this 1D value with 4 bytes of 0 or 3 zeros after it. So that these 4 bytes right here are probably our 32-bit immediate that we're loading into this register. And so if we wanted to change all of those, we could come into our program and then input this 1FC7 offset, or I guess it would be 1FC7 plus 1, so 8, 9, A, and B, it's looking like, are going to be that last nibble. And if we come in here and do that, we can change those bytes. And so I will demonstrate this very quickly. So let's change the windows again. Let's go back to here. And also back to there. All right. So now let's do this. Let's GDB this again. And if we once again take a look, we can disassemble main. And we can look for that read call that we were targeting, which is at 1FC7, which remember that when you're in here and you disassemble a function, you'll get all those offsets that will line up. So we can see that 1FC7 is that move EDX 1D. And if we really wanted to take a look, we could look at the specific instruction, so XGX, and then maybe show us the 8 bytes here. So we can see that we have that BA that we were talking about, that 1D, and then 3 bytes of just null. So this is presumably going to be our 32-bit immediate that we're loading in. And so we can now modify this. You might need to know the value of 1FC8 in non-hex. So it's a Python job. 1FC8 is going to be 8,136. And so let's try that and see if we can see one of our bytes change. So here we are going to, I guess, let's do that. So we'll run it. We'll give it this offset. Oh, I guess it says offset in hex, so I didn't need to do that. So 1FC8. And then we're going to give it a new value. So we were previously at 1D. Let's see if this is in bytes or maybe here. So we can see that it's just become equal to B. And let's take a look at what that actually looks like. Oh, oops. I have to do XGX star main plus that. Oh, wait, that's not how that works. Dysys main. But basically, we should have seen our instruction mildly change at that 1FC7 offset. Now that we've actually started our binary up, we have addresses accounted for all of these. And so we are looking for the FC7 ending. We can see we have now changed this to move EDX and then a B because we put a B in. And so now we've changed that 1 byte. And so at this point, the question becomes, what bytes do you change and why? And I will leave that as an exercise up to you. Is there any way to just print out all of the stack values? X40GX RSP. If you're using Gef, you can also type like context and you'll get a decent stack layout up here. But generally for me, this is just examining and then some large number GX and then just looking at RSP. And then if I'm trying to figure out what pointers are, what about the contents in the specific address? Well, I mean, you can give it a specific address if you do XGX, like, oops, I killed my GDB on accident. So if we looked at maybe a long thing here, and so maybe I want to figure out, okay, well, what is the other nice thing too is you can also do info frame, which will give you information about the current stack frame. So you can see that it's telling us that this saved RIP for our read call is this value, which we can also see is currently the top value of our stack. And so if I maybe wanted to figure out, okay, well, I know that this is a return address, but where's it pointing to? I could maybe look at that instructions like x/I, give it that address. We can see we're coming back to this IO new file underflow function, whatever that's doing. I could also just click on an address here maybe and decide that I want to look at the contents with like x/gx here, or maybe if I think it's an instruction, x/I, which maybe it is, maybe it isn't. Maybe if it's string, probably not a string, etc. But you can just kind of toss memory addresses in everywhere. Awesome. All right. Next questions. Who is next? I'm waiting on a question. Let's see. Does anyone else have questions? Trying to think if there's anything useful I can demo too. What are the solve counts looking like for these? 13 for Rev. Who is solving 15, 16, and 17 and 18 without solving 13 and 14 and 15? Maybe they were working off of previous weeks. All right, so let's take a look at 13. Yeah, I'm thinking they did it in the archive. Crazy people getting a head start. I will also talk about 5 and 5.1 in a second too, as well. Let's quickly look at 13 though. So if so 13 is your, if I remember correctly, it's the first Yon 85 level. No, it's the second Yon 85 level. And so I don't really have a ton of specifics on what I want to go over with 13, I guess. So I guess like what's your specific question about 13? Or I guess like what's tripping you up about this one? I'll load this one into Ghidra too, just in case. Never mind, forget about 13. Okay, I can do that. Just I guess to give a quick, I guess, hint on 13 in case someone clicks on this hoping I talked about it. Basically for 13, you are doing exactly what you did for 12. It's just harder. That's it. And so in 13, um, quite literally, you're doing what you did for 12, except it's harder. And the main thing about these Yon 85 levels is that it's really easy to do the teaching challenges if you just stare at the output. But the thing is that you should learn how to do this from the perspective of you open your reverse engineering tool and learn how the program works and make guesses about what happens. And I guess I will circle back to this after I talk about 5, because I guess I can give some reverse engineering advice. So let's talk about 5 really quick. So the question is for 5.1, for 5.0 and 5.1, are they mangling input in the same way? The answer to that question is it is random. So you can have a set number of manglers, or a correction. I guess I need to recall which challenge 5 is, but if 5 is multiple manglers, they can all be different. And if it's one specific mangler, if it's introducing one specific one, then it's probably that one. It XORs the input. Well, so it's going to be random, like what it's XORing, if it's doing like sorting, swapping, etc. for everyone. We've randomized all of those binaries in that way. So don't use like your teaching binary to make assumptions about the testing binary. Instead, you should just look at what each of them is doing. And yeah, you can find out what it's doing by pulling this up in a reverse engineering tool. So I don't see that much wrong with at least trying to look into solving 5. So let's take a quick look at 5. I won't solve the entire challenge, but we can at least get an idea of what's kind of going on. So I'm going to open this up in Ghidra, and then I will throw it up on the screen in a second. All right, let's change this window. And then let's also change this window. All right, everyone should be seeing Ghidra now. So the first thing that we need to do is make sure that you auto-analyze when you open up binary in Ghidra. Just come up here to analysis and auto-analyze. It usually will display a pop-up asking you if you want to do it or not. But just make sure you do that, because that's what's actually going in here and like decompiling all these functions. And let's just take a look at main. So if we come over to our symbol tree, open up functions and go to main, we can come in here and start looking. Now, I know that so if we take a quick look at what's going on, we can see that we've got some puts coming out. So here's our printout ready to receive your initial license key. We can see that we're reading into this local 16 buffer. It's giving us our initial input. And then right after this, it says, this challenge is now mangling your input using the XOR mangler with the key 9B. And basically the question is, or I guess the point of these teaching challenges is so that you can come into a reverse engineering tool and we tell you, this is exactly what the program is doing at this specific point. And then the code that actually does that shows up. And so this way you can say, I know what this code is doing. It's going through my input and mangling every single byte with 9B, or mangling by XORing every byte with 9B. And how can I determine that that's actually happening? Well, let's take a look really quick. So the first thing that we can see is we read into this local 16 buffer. And so I'm going to come over here and rename this. So just I can click basically highlighting it, and then I'm hitting this N key on my keyboard. So just highlight N, and I'm going to rename this to input buffer. Boom. And note that I know what this is. I can retype this variable. It is not undefined for, it's a character pointer, because that's what we feed to our input buffer. Now, sometimes this can generate some weirdness in Ghidra. It looks like we have two different variables that are getting merged together, which is interesting. Oh, I see. It's instead giving us a character array of the bytes that we enter. And as we can see that we're reading in a max of 5 bytes, so that's why this is 6 bytes long. So this is not actually undefined for. This is a character array of 6. There we go. Cleans up pretty nicely. And that is basically mangled our decompilation a little bit, but yeah. And so now that all I've done is I've made some basic assumptions about the program. I said, okay, here's my read call. It's reading from standard in, that's FD0. It's reading to here, and it's reading 5 characters, which In most cases, it means you need at least 6 bytes of storage to put it there because you have your 5 characters that you've inputted and then your trailing null byte, usually. And at this point, I made the assumption that this input buffer, by retyping it to a character array of 6 long, just as an initial guess. And after doing that, my decompilation has completely cleaned up. Like, look at how nice this code looks. And just like, I'll undo that operation. Like, here's what we went from. Like, byte, pointer, long pointer, address of this plus that. Like, what? Like, you can find out what it does, but it's much easier if you just come in here and tell Ghidra to interpret it correctly. And so now we're looking at for local 28 equals 0. Okay, well, local 28 is a bit wordy for a variable that's basically I. So for I equals 0, I less than 5, I equals I plus 1. And here we can just see that now it's input buffer at I equals input buffer at I XOR 9b. And just by very quickly coming in here, changing some solution or changing the types of my variables around, I very quickly made the answer fall out of the decompilation. And the other thing to note is that you can also look at this and see this in you can also see this here. We are XORing EAX by 9b, and then we are putting it back in. That FFFF is just because we are only wanting to XOR this last byte, because we're doing it 1 byte at a time. And so you can either find it in the assembly, or you can also find it in the decompilation. Both are valid solutions, both work well. All right, so with that in mind, I want to jump back over to 13. And I want to talk about just some, I guess, reverse engineering advice. Let's go with that. Let's go with the word advice. Let's see, stream's still running. Cool. All right, so let's close out a level 5. And then let's analyze this and come over to main. So in these Unity 5 challenges, you'll note that there's a lot going on, and you're going to be very quickly thrown into pretty complex reverse engineering challenges. And so the main thing is that you want to make things easier for yourself by trying to reverse engineer in a sane way. And I'm going to spend a little bit talking about this, so if you have questions about other challenges, feel free to interrupt me. But otherwise, I'm just going to start rambling. So when it comes to reverse engineering, there's a couple different strategies or ways to think about it. Some people will figure out, okay, what's the intended goal of this program, and then work backwards. Other people will figure out, okay, where's the entry point of the program, and then work forwards to their goal. Sometimes you have a specific goal in mind, like obviously we want the flag out of this program, and so we need to figure out, well, where in the code could possibly open up our flag, and then we could work backwards from there. But if you're just going from the purpose of generally understanding a binary better, some specific advice that I can give is try not to get zoned in on what every single bit and piece of each program is doing. It's really easy for a beginner reverse engineer to pull up something like this and then start at the top and trying to understand every single line by line. And what that's going to result is you're going to be sitting here going, okay, well, what is fs colon hex 28? What is this? I don't know what this is. Or I don't know what stack check fail means, or I don't know why I'm casting all of this. Like, what the heck does set bbuff do? And the advice that I can give is focus on understanding the program at a broad level. Like, people who are reverse engineering and are pretty optimized at this are coming in and saying, okay, main is printing some stuff, main is doing some things, main's calling some functions, and they're thinking about it in a broad sort of a broad way. So we can see that here we're doing some printing. It looks like we're doing some minor setup, but if we kind of look, this is a lot of C code for what is not a lot of assembly code. And so we can see that we have this weird stasq rep instruction that's happening that's representing an entire for loop. That's probably doing something interesting. And if you look really quickly, we can see, okay, local 118 is being passed into this execute program function, so we probably remotely care about its value. And we can see that it's being set equal to this puvar2, and it's looked like we're looping over it. We're setting this dereference of this to 0. If I had to make a really quick educated guess, I would bet that we're zeroing out this local 118 that has been defined as like this massive chunk of memory. And we could also then go look at execute program. And basically you're jumping around, you're looking for essentially just broad overview of the program. Like I'm looking at execute program going, okay, well, it looks like it's executing the program. This to me looks like a program. And you can then come in here, okay, well, what is interpret immediate doing? And conveniently, it prints it out for you in the teaching challenges. We can see, okay, well, it's clearly saying the immediate of this, which is uvar1, which it looks like we're getting from this describe register function. And so and we're passing in param2, and then we're setting that equal to something else, etc. We have this write register functioning happening, which is passing around param 1, 2, and 3. And so the questions for you just become, okay, well, what are these parameters looking like? What are they doing? Like, what's happening? And it's nice to kind of like hone in your focus, but just make sure that you're not trying to like pick apart the program at such a level that it just doesn't make sense to try and understand it at that level. You should have like ideas of what this is doing. Like eventually you could decide that maybe immediate is setting like param2 equal to param3 or something like that. But obviously it's slightly more complicated than that, but there's just a whole bunch of different like ways and paths for you to go down. And the other thing is, if you know what types things are supposed to be, make sure that those types line up. So a really like quick and dirty example is printf, right? Printf is taking uvar1 and param3 directly into it, and then we get format specifiers of the %s and then %hhx. If you don't know specifically what these are doing, you can Google them because these correspond to data types. And so it turns out %s is going to be a string, which we know that uvar1 then in C has to be a character pointer. So we come up here, we retype our variable to a character pointer. And we also know now that describe register probably returns a character pointer. Continue, etc. And now our values have gone from this really bizarre garbage from, oh, it's taking the address of this. And if I look at this, it's a byte that corresponds to A. But now telling it that we're returning a character pointer by retyping our function has informed Ghidra that now we're just actually grabbing those string literals. And now we have if param1 equals this value, then we return this at the end. Like, once again, you've retyped something and the answer has fallen out of your function. And so it turns out that this param1 is probably corresponding to a register. So reg, or maybe like reg value, you can reg identifier, you can call it whatever you want. It's a char, obviously. And yeah. But the nice thing is because we know that this now is taking in a char, we can come back to our function that we were looking at, which was interpret immediate. And we now know that this second parameter here is a char. It looks like it's found that out for us already. We can also see that param3 is a byte, but then getting converted to a long. So maybe that's something also to take a look at. But basically, you're just essentially solving a constraint problem. Like if you want to think of it like that, you can think of, I've found this one piece of information. How can I propagate it to my program in a way that makes sense? Similarly, like other places that call this describe register function. So for example, in Ghidra, when you come and look at a function, you can, at the very top, it will show you the xrefs for that function. So here you can see describe register xrefs, and here's all of the places in my entire binary that this describe register function is referenced. So here's that interpret immediate usage we were talking about. But if we go back, our second usage is also in interpret add. And because we have retyped this function, every single return value that this function has gone has now propagated to a character pointer. Like we don't need to go in and change all of these now because we changed the return type for a function. It just fixed everything. Similarly, like read register, it's returning this ulong. We could look into that. Ulong byte pointer, like a whole bunch of insanities happening everywhere. And so don't hone in on the super specifics. Don't try and figure out exactly what everything is doing. Instead, get broad understandings, make assumptions, and if you need to deny those assumptions later, that's okay. Like it's completely okay to be like reversing, and then at some point you're like, okay, well maybe that's not actually what this function is doing, and then you come back and reevaluate your assumptions. This is much better than you're sitting there and basically trying to invent the wheel in every single function, where you're trying to get like a Newtonian physics level of understanding of all of the assembly that's happening. Just don't fall down that rabbit hole. That's my advice. Um, Specifically, I'm pretty sure you can get a lot of advice in specifically the Discord for asking about how to reverse things. We have a lot of really good reversers in the Discord, and so those are the kind of questions that like they would be happy to answer. And so hopefully that gives you a little bit on some reverse engineering. Basically, just like renaming and retyping variables in Ghidra is really important. It helps Ghidra do a lot of the decompilation better. This applies to other reverse engineering tools as well. I'm just using Ghidra because it's the one that I used in this class. I personally use IDA now, but I did the class with Ghidra. Does anyone have like questions about using Ghidra, or maybe just reverse engineering in general? Like, is there some stuff that you're running into that you're maybe unsure of how to like navigate? Or maybe you've run into like one of these functions and you're looking at it and you have like, I have no clue what's going on here. Like we could look at some of those. Is there a list of shortcuts for IDA somewhere? Generally, all of the shortcuts in IDA you can find kind of like just by like looking. I think IDA does the thing where it like shows you the shortcut next to like what it's doing. But I'm pretty sure there's got to be a list of IDA shortcuts somewhere. I know for a fact off the top of my head, the main ones that I use is like renaming variable. Yeah, I found it. If you look up there's actually a cheat sheet for this on the IDA Pro website that I'll link in the chat here. That's literally if you just Google like IDA shortcuts, then it was like the first link that popped up for me. But that hopefully can help you. And then let's see, our another question is 7.1 has had me stuck for a while. So 7 is going to be one of those challenges that's slightly different for everyone. So let's take a look at my variant. It's not different between IDA free? No. That would be insane. I would not want to meet the developer who decided that keybinds between the pro and the free version were different. All right. So if we look at 7.1, 7.1 is just another license key verifier. However, we don't know what it's doing. And because we're in a testing challenge, we have absolutely no concept of what it's doing yet. So the first thing I'm going to do is download this and open it up in Ghidra. I know I'm not showing my screen right now. I know I'm showing Ghidra just because I'm going right back there. So let's load this one up. Yes, analyze. All right, showing Ghidra here, showing Ghidra here. Good. All right. So analyze this. All right. So now, first things first is we have a binary that looks like it has been stripped. And to confirm like if you have a stripped binary or not, all you can do is run file on it. If you run like file and then your binary, it will tell you if it's stripped or not. It'll say like stripped at the very end. And basically, if you have a binary that's stripped, you don't get a lot of symbols. And we can see this because none of our functions actually have names. Instead, they're all just identifiers. And so the first question that you could ask yourself is, well, which one of these functions is main? And it's a good question because obviously I could click through every single one of these and find out which one's main pretty quickly because there's only 7. But what happens when you have a statically compiled C++ binary with like 500 functions in it? And so knowing how to find main from just like your program in general is a really nice skill. And if you look at basically libc start main or your entry function, basically we make a call to libc start main, where if you look, basically go to the xrefs for this. So in here you would find, where is it? There we go. You would find your imports. You would find libc start main. We would go look at our xrefs to find our entry function. And in your entry function, you make a call to libc start main that follows a very nice convention, which is that this first argument right here is going to be a pointer to your main function. And if we click on this, we can see that indeed it is a pointer to our main function. And so whenever I'm dealing with a strict binary, the first thing I'll always do is come look for libc start main and just rename this first element to main. And now we can start looking at it. So as you can see, this is that classic license verifier software that will allow you to read the flag. It looks like we're reading into this local 38. So let's do what we did last time. We discovered that local 38, which is right here, was a character array. And it looks like we have hex 19 characters as input. So we're going to get hex 20 as the total length of our array because we need room for that null byte, which is 32. So if we come up here to this local 38 variable and just retype it, we can turn this into a character array of length 32. And so now we can very clearly see, and we can rename it too. So let's call it input buffer. And so we can see this little bit of a weird construction right here, but this is just how Ghidra represents like accessing like different widths at different locations. If you actually look at the assembly, we can see that we are basically just zeroing out the entirety of the input buffer. So we're moving 0 to the keyword pointer of the first 8 bytes, second 8 bytes, third 8 bytes, and then the last set. And so basically we're just zeroing out our input. And so let's continue looking at our decompilation. So ready to receive your license key. We got our input buffer, and then it looks like we instantly do a crap ton of interesting operations on our string. And this right here, like, this is the programmer's worst nightmare. You know, you just see a ton of code. It all looks like math, and there's no print statements. Like, this is hell to me, at least. And so for me, it's all about simplification at this point and figuring out how can I split this up into blocks, what's going on. And so my instant intuition for me is going to see, okay, well, I see a whole bunch of for loops. And so I'm going to start breaking these up mentally into chunks of like, okay, what is this for loop doing? What is this for loop doing? And so just kind of like breaking it up in like bite-sized pieces to digest. Because once again, like all of this together, insanity, don't want to think about it, but one for loop, I can handle this. And so right away we have for, and then we have some looping variable. I'm just going to call this I, and because it looks like we have quite a lot of i's, I'm just going to call this I_1, or you could call it like I1, whatever you want to call it. And then if you're someone who likes to, depending on your work pattern, like I'm crazy, and so I'll come in here and like rename all of these right away just because I don't want to forget to do it later. Note that I'm renaming them with numbers at the end just because I'm, at least in IDA, it will yell at you if you name them all the same. Yeah, duplicate name. And so in our first for loop, we can see something that's going on. So for I equals 0, I less than 19, I equals I plus 1. So first off, we have a loop that is iterating over what appears to be our entire string. Because we read in 19 characters, or hex 19 characters, and that's what we're looping over. We then see that we have this ivar2, which is going to be equal to I mod 3. Not sure what that's doing yet. Let's keep looking. So we have if ivar2 equals 2, it looks like we are going to XOR our input buffer by 8D. And then else if ivar2 is less than 3, if ivar2 equals 0, then we are, or sorry, yeah, if ivar2 equals 0, then we're going to XOR by 95. And if ivar1 equals 1, we're going to XOR by F6. And so if we abstract away all of this for in our brain for now, and we just think about this ivar2, and we think a look at our possible I values, we know that I is going to start at 0, and so we're going to get 0 mod 3. And 0 mod 3 is just 0. And so on our first run through, this ivar2 is going to be 0. And then we add 1 to it, and so then we'll get 1 mod 3, and so we'll go to 1. We'll also then go to 2 mod 3, which will be 2, and then we'll hit the case where we hit 3 mod 3. Now, 3 mod 3 is 0. And so it looks like we are basically just kind of using this to keep this I value in the range of 0, 1, and 2. And so if you, and once again, like this is one of those nice things too, because like we have pretty legible C code. And so if you were really unsure about what this was doing, you could literally pull this out and run this code in like C or Python and print out this ivar2, and you would end up seeing 0, 1, 2, 0, 1, 2, 0, 1, 2, because that's what we're doing. And essentially, we're saying, okay, well, we're XORing basically by a key. And that key, it turns out, is going to be the 0, 1, and then that 2. Because we're XORing the first byte, or a byte at the 0th index by 95, byte at the first index by F6, and then byte at the second index by 8D. And then that process is repeating because of this mod 3 that's happening here. And personally, I'll insert a comment here. I guess you can't see the pop-up, so I'll type fast. We're basically XOR by key, OX8D, or OX95, F6, 8D. And essentially, that's what we're doing. And then this is basically just repeated out. You went to parallel construction, this loop? I don't know what that means, I'll be honest. Oh, build it in Python? Okay, yeah, I can do that. So if we wanted to, like, literally, like, and so, I mean, I guess we'll do that at some point, since we're going to put this in Python. So for now, we'll, does that make, yeah, I guess we can do that. Let's do that now. Sorry for confusing everyone. So now that we kind of think that we know what this is doing, we can actually look at confirming exactly what this is doing. And so one of the nice things about working with all the tools that we do is that they all interface pretty reasonably. Like, I know that I'm going to read into this input buffer here, and then I'm going to mangle it with this key, or at least I think that's what's going to happen. But what we could do is we could say, okay, well, after this for loop, let's look at the input buffer and see what actually happened in GDB. And then we can confirm if we are actually XORing by this key or not. So let's switch back over to our web interface. Here we go. And let us make a file. So it's cd home / office hours, make your baby rev. And then touch 7 point, I guess 7.py, sure. And then let's locate this garbage. Where are you? So ours baby res 7, right? And so let's go ahead and begin to think about this. So first thing that we're going to do is, let's make sure, okay, good on the recording, good on Discord. Okay. So we decided that we thought that they were XORing our input by this key. And we also know that our input length was going to be OX19. And so let's just go ahead and take that out. So let's just say that our input, in this case, we just want it to be something simple. And so we will just say our input is A times OX19. So we're just going to get a ton of A's. And from here, I guess I probably shouldn't redefine input. So let's say my input. And so now we want to reconstruct that for loop. And so I am literally going to go copy that C code that we got out of the decompilation and put it right here. So here's that C code that we got from Ghidra. Clean this up just a little bit. Don't need that there. This else if ivar2 is less than 3 is kind of irrelevant. Basically, I'm just cleaning up. Like, we know that based off this being modded by 3, it will never be greater than 3. So you can just get rid of that. And then this can become an else if. And then if you really wanted to reorder these and all that fun, you could also do that, etc. But now let's make this in Python. So here we have a for loop that's going from 0 to hex 19. So that's just going to be for I in range of x19. And then we are going to go ahead and then calculate this ivar2, which is going to be I mod 3. Don't need a semicolon because we're in Python. and then we can just copy out this loop construction. I'm going to do it from 0, 1, 2, just because I'm not crazy. So we'll say if ivar2 equals 0, we'll do something. Elif ivar2 equals 1, we'll do something else. And then elif ivar2 equals 2, we'll do something else. And what is that else? Well, this. So that's going to be our, so here's our 0 case. And I guess we can call our input buffer to make things a little bit easier. Get rid of our semicolon. Bring that guy in here and bring our last one in here. We're gonna sanity check ourselves really quick because one of the most common mistakes that you can make while doing reverse engineering in this kind of process is doing exactly what I just did and then being lazy and not double checking that you copy pasted the right things. I've lost many hours of work to this. So it's something that I'm conscious about. So ivar2 equals 0. We're XORing by 95. 95, check. For 1, we're XORing by F6, check. ivar2, or for 2, then we're getting that 8D, check. And then finally at the end of this, we would want to print out the input buffer. And then I guess we can also print out before, so before XOR by key, and then that's OX 95F68D. And then let's print out our values. We can just say input buffer. And then we'll copy this guy down here. And we'll say after. One thing that I like to do when I'm interacting with like bytes like this is to pass everything to like the repr function, which this will basically represent non-printable bytes as just hex, so that way you don't get like random characters on your terminal that you don't know how to interpret. And so now we can look at running this. So python 7.py. Oops, bytes object does not support item assignment. I should have seen that coming. So we need to turn you into a list like that, I think. And we might run into a wrapper buffer for bytes and int. So let's convert this to an int. And let's see, I think we finally probably need to convert those two characters after that. Valid int for base 10. What am I doing with my life right now? Oh, duh, this should be that and that. There we go. Okay. And so here's our input key, and then here's our output. And these are not in hex, so let's get them in hex. I guess I'll have to use string constructions. We'll just say this dot join. Let's see. I don't program fast anymore. This dot join hex of x for x in the input buffer. Oh, I need to not use big quotes. There we go. And then I guess we can also reuse this that we just wrote for up here. All right. Store object cannot be. Oh, okay, whatever. It's because they're not converted right up there. It doesn't matter. We know they're A's. All right. And so here is what we would expect to be seeing. And as we can see, it's a repeating pattern of D4, B7, and CC. And so now we want to confirm this assumption. And so let's head into GDB. So GDB/challenge. And I'm going to disassemble main. Oh, that's right. We're in a strip binary. So when you were in GDB and you have a stripped binary, you can't get away with simply just breaking on main or trying to disassemble main. You don't have symbols to reference. And so instead, what I'll use is start. And start is going to attempt to put you at some location. Now, I'm saying some location on purpose because when we're in Gef, we can figure out where we are pretty quickly. So I know that I'm currently at this address, which is an NBR64 instruction. If I take a look at my mappings with VMMap, we can see that we're at 55D13D82A, and we can see that that's very clearly in the code segment for this binary, because it's executable, and that's where we are. And then so if we wanted to figure out specifically where we were in here, we could then go look for specifically for this 200 offset in Ghidra and figure out exactly where we are. What I can tell you though is that we are currently in our initialization entry point function, because if you were to go look at Ghidra for this specific challenge, you will see that the entry function that contained libc start main started at 1200 offset, and we are at that 1200 offset. Let's do that. And then once we get our function offset, which we are then going to disassemble by looking at a ton of instructions. And let's take a look. So here we can see that we're doing our call instruction. And basically I would expect that we have our libc start main call around here in here somewhere. And what I'm doing right now is I'm literally like tabbing into my Ghidra and I'm looking at the disassembly in my Ghidra and then lining it up against what I have here. So I'll quickly copy and paste out what I have just because I can't show two windows at the same time. That's my one limitation that I've got going on here. So here's my Ghidra output. We can see that we're at this NBR64. Here's our XOR EBP, move R9, etc., etc., etc. And then we see these three LEAs, of which we renamed the bottom one to main. And so this indicates to me that this bottom LEA, this address right here, this A412 at the very end, is going to be main. We can confirm this because we know the last three nibbles are going to be the same. And so if we go look at what we thought was main in Ghidra, we can see that, I'll copy this out again. We can see that main, the NBR64, so the start of main, is at that 412 last three nibbles. And once again at 1412, so we knew the previous function was at A200 or 1200 offset, so you'd expect this one to be at A412 offset, which it is. And so here is our main function address. So we could come into here, say disas here, not that x50i, not pointing to either, just like that. And then now we're in the function of main. And so that's how we can find out where main is. The other way is that we also know that we have a blocking read call in main. So if you just hit R and it says ready to receive your license key, that is also in main. We can control C out and find out that, hey, libc start main called main, and it tells us where main is. And then here's the instruction that we're at in main, and then we called our read call. Now, we are about to put in a ton of A's into this read call because that's what we put into our Python script. And that's what we confirmed up in this Python script. We put in A's, we got some expected values out, of which I don't remember, but we can find out in a second. And so what I want to do is break in main. So if we take a look at 50 instructions from this point, which if you are in Gef, this bottom point is going to show you your backtrace, where basically we can say, okay, this function was called from this function, was called from this function, and basically these are the return addresses of where you're going to be going back to. So, one second, I got to plug in my microphone, it's about to die. Okay, there we go. So if we take a look here, 50i here. Here at this E546, 546, we can line that up in Ghidra to find out where we are. So if we take a look, I will copy this up here again. We can see that 546, we have that read call, and this is the read call that's reading in our physical input. So that's the input buffer that we were talking about. And then right after that 546 is after the read. And so what I would do is I would come into Ghidra, find that for loop that I just rewrote, this guy here, and go to the end of it. And I would find that the last address in there is 5BE, it looks like at the very end. Maybe 5C2. And basically we would find that location. I'm scanning for it. It's a little bit hard to pick out with loops sometimes. Especially when you, if you have IDA, by the way, it's really easy to find loops because you can look at the CFG. I wish I could show that easier, but I can't. But essentially what we can do now is just watch our input buffer. So we can see that we called main with fd0, buffer equal to this, and here's our n bytes. Here's our buffer. And if we take a look at x, I guess 4gx is what we'll need. We can see that right now it's all zeros, except for some junk over here, which we don't need right now. So now let's read in a whole bunch of A's to this. So now that I'm broken in my read function, if I type finish, it's going to run from exit until that. I'm going to feed in a ton of A's. And then now let's go examine that again. We can see here all of our A's have popped up. If I do an x/s on this specific address here, we can see all of our A's. A repeats 25 times. And so now we can start stepping through our function and looking to see how our string is mutating. So I'm going to keep this guy on my clipboard right here. And then I'm just going to simply start doing a whole bunch of SIs. If you specifically know where you need to break in here after you're done, you can also do that. If you're someone who just wants to watch the effects of what's happening, looks like nothing's happened yet. But let's see, can I maybe shoot down a little bit? Let's just start scripting a dramatic amount of instructions. So I did SI 50, step forward 50 instructions. We can see that now we have this B7 D4 down here. Let's skip another 50 instructions and look again. So now we have CC B7 D4. Let's go again. And so now we're starting to see that pattern emerge. And so the question is, well, is the pattern that we find here the pattern that we were expecting earlier? And so let's go take a look. So open a new terminal. Let's go to that office hours folder I had. 37.py. And we found that when we inserted a whole bunch of A's, our expected output was D4, B7, CC. And then those 3 bytes would repeat. And here we see D4, B7, and CC. Note that those are just swapped because of you're viewing this in endianness, little endian. But basically, we are getting the output that we expected to see. And so now we have successfully reversed one of the manglers because we put in the bytes, we got what we expected to get. Basically, all of the assumptions that we have made, I have confirmed. And so now we could continue and then maybe look at the next one and the next one and the next one. And then basically we're just going to go through and reverse them. Because remember that once you actually get all of these, once you actually come in here and write all of these, all you have to do is apply them in reverse order, and you can go backwards from your expected license key to your input. But I don't think I need to show every single one of those. If it's a symmetrical function, yes, it has to be reversible. Not all operations are reversible, unfortunately, as you will discover. Does anyone have questions about that? All right, don't think I have any questions. Does anyone have other questions about the rev levels, any of the GDB levels, any of the, I guess, literally just anything, because I'm going to be wrapping up soon? Want to go over a bit of 9.0? I think I talked about 9 a little bit, but I only talked about how you could maybe accomplish 9, but not actually like what you would look for, so we can also talk about that a little bit. Basically, I talked about how to find offsets, but I didn't talk about like strategies of how to actually approach the problem. All right, so let's take a look at 9. What happened? There we go. So here we've got Unfortunately for you, this license key cannot be reversed. You will have to crack the program. And so, second I got pinged. Okay, good. That's not anything relevant. Okay, so unfortunately for you, the license key cannot be reversed. You'll have to crack this program. Now, generally, we try not to lie to you in these program outputs, and so there's a very high chance that this license key actually cannot be reversed, and so we'll have to do something interesting. And so what we're given is this cute little interface where we can change bytes. So we're offset hex to change, I don't know, 1. New value in hex, I don't know, 56. And then it tells us that this byte at this address has been changed to 56. Now, remember that this is the address of our binary. We gave it an offset of 1. So this will apply to give it offset of 0. We can see that the exact base address of our binary. So this is where our binary is loaded in. And so the question becomes, how can I byte edit this binary with 5 bytes to spit out the flag? So if I can change 5 bytes anywhere in this code, after that will be run after this, obviously, what 5 bytes do I pick to get the flag? And so let's open this up in Ghidra. So let's go back here and go back to here. Let's take a look at our main function. And basically we have this massive function, and let's quickly take a look at what's actually going on. So it looks like we're ready to receive our license key. We can repeat some of the same things that we've been doing already. We know that local 38 is once again going to be a char array of 32. We established that a little bit earlier. We also know that it's going to be our input buffer, so we can rename it. Let's see what else we got. It looks like we are MD5ing the key. Interesting. So, yeah, I would go ahead and wager that you're probably not going to want to attempt to reverse MD5. And so the question becomes, well, I still want to be here in the win function. And so how can I patch 5 bytes from essentially, let's go from here to, I guess, here to figure out how to get in here. Now, you're given 5 bytes. There's a couple of interesting things that you can do with 5 bytes. So there's a lot of, I guess, like fun solution paths. Trying to think how much I want to give away specifically. So I guess, like, do you have any specific questions about 9? Like, what's tripping you up about 9? Do you want some advice on like, how to approach it? Some more of the whole offset thing, but I joined late, so I'll rewatch. I've already gone over that. Okay. I guess as a really quick way for just like if you're looking at this in Ghidra and you want to find the offset of literally anything, Ghidra has this great feature where, let's say that for some reason I want to, let's pick something interesting. Yeah, let's say I want to change like 1D again. If you come in here and look at the specific place that you want to change something, so say that you want to edit one of the bytes in this instruction, if you mouse over this little bit right here, then this number, it will show you the exact offset. And of course, I literally can't figure out how to show you this at all, but I swear if you put your mouse here and leave it still, a pop-up window will show that says image base offset. And also, if you come up here to the very top of your file, you'll see that it's loaded in with a base address of 100,000 in hex. And so at any point, you can just say, okay, well, the address of anything in here minus 100,000 is my offset. So if I wanted to maybe modify this printf call, it's 1f79 is going to be my offset because it's just 100,000 minus 100,000 1f79. And then you would feed that into your program. And then you could also find this in GDB, etc. But basically, you're just giving an offset, so it's always going to be the same every time. Uh, awesome. Okay, so does anyone else have any, I guess, last minute questions before I wrap up? Okay, sounds good. All right, I will see everyone here next week. Make sure you guys start on Rev early. Rev is probably one of the harder modules that you will see. It's also the most relevant module, probably, besides shellcoding, because you'll be reversing every challenge here going forward. You will no longer see source code in any of the challenges. So get used to reverse engineering. It's worth it. And with that, that's all I got. So I'll see y'all next week.